In this video, we're going to talk about how to determine the volume using the shell method. We know how to find the volume when we're using a disk or a washer method, but what happens when that radius, we don't know the bounds? So in this picture, I have y equals 2x squared minus 3 is my function, and I'm trying to find the volume when I rotate around the y-axis. So here's my shape, and when I try to make my disk, I find that I don't know what the radius is because I have my left bound and my right bound, they're the same curve. So if I try to subtract them, it's not going to work. So instead of doing this, we can use what we call the shell method. So our shell method is thinking about if you had a soup can and you wanted to peel the label off it. We're looking at that outside shell, so it's a cylindrical shell. So we make the height of our shell the height of our curve as our curve progresses. And then we have the radius of our shell is from our axis of rotation to our height. And we know that the finding volume for a cylindrical shell, that's just the outside edge, so essentially it's just 2 pi r, which is the area of the circle, times the height. So if I take this cylindrical shell and I flatten it out, like I said, to get that area of this, it's 2 pi x times its height, which is f of x, and then we're going to have our thickness, and then we're taking the limit of all of these shells as I keep putting them together to find the total volume. So we have the integral from a to b, the circumference 2 pi x, where x is essentially the radius, the height, which is our function, and d of x for the thickness. So let's actually find our volume. So we know our bounds are from the left to the right region, so from 0 to 2. We have 2 pi times our radius, which is x, times the height of our function, 2x squared minus x to the third, times our thickness, dx. And so now we're going to integrate. So cleaning this up, I'm going to pull the 2 pi out front. So I have 2 pi, the integral from 0 to 2, of 2x to the third minus x to the fourth dx. So when I integrate, I have 2 pi times 1/2 x to the fourth minus 1/5 x to the fifth. And I'm evaluating that from 0 to 2. So I have 2 pi times 2 to the fourth is 16, half of 16 is 8. 2 to the fifth is 32, so minus 32 over 5. And then I have to plug in my 0, so I end up with 0 minus 0. So I get common denominators, so I have 2 pi times 40 over 5 minus 32 over 5. So I have 2 pi times 8 over 5. And I find that this volume is equal to 16 pi over 5 cubic units. All right, let's try another. So here we're finding the volume of the region enclosed by y equals x squared, y equals 0, and the line x equals 2. And we're rotating it about the y-axis. So we're finding this region in here. So my radius is still x because that's from the y-axis out to my curve. My height is equal to the y function, which is x squared. And I'm integrating from 0 to 2. Okay, so my volume is equal to the integral from 0 to 2 pi times my radius, which is x, times my height, which is x squared, dx. So I'm going to pull the 2 pi out front. So I have 2 pi times the integral from 0 to 2 of x to the third dx. So this is 2 pi times 1/4 x to the fourth, evaluated from 0 to 2. So 2 pi times 1/4 is just going to be pi over 2. 2 to the fourth is 16. 0 to the fourth is 0. So this area is equal, or excuse me, this volume is equal to 8 pi cubic units, again using our shell method. It's also possible to make these rotations and not use a coordinate axis. It's really going to change the setup of our radius. So here I'm looking at just this little region. It's kind of hard to see because it's already been rotated. We're just looking at this little region here that's going to get rotated all the way around to kind of make a cone. So if I'm using my cylindrical method or my disk washer method, I can still do that, except the radius is going to change. Because as I can see right here, my radius at this lowest point here, this little line is my radius, but to get that radius, I'd have to go from the A minus whatever that value is, which is an x value. So my radius here is going to be A minus x. Now, if I'm using my shell method, we keep the same basic concept. It's 2 pi the radius times the height times the thickness. So in this case, my height would be f of x minus g of x, not just a straight function, but we'd still go through and evaluate the same way. Okay, so here we want to find the volume of our solid generated by revolving the region around the curves y equals 1 over x, which is the blue line, y equals 0, which is the x-axis, or excuse me, the x-axis, x equals 1, and x equals 3. So this yellow region, we're rotating around the line x equals 3. So I can still make my shells. So there's my shell, and I can see my radius is whatever this 3 value is minus whatever the x value is, because from 2.5 to 3, my radius is 0.5. 3 minus 2.5 gives me that 0.5 radius. So I know my radius is equal to 3 minus x. The rest of our setup stays the same. So we know our volume is equal. We're going from 1 to 3 on my x's. It's 2 pi times my radius, 3 minus x, times the height of my function, which is 1 over x dx. And then I'm integrating. So I'm going to pull out that 2 pi. So I have 2 pi, the integral from 1 to 3 of 3 over x minus 1 dx. So now I have 2 pi times the integral, or excuse me, the solution that when I integrate, I have 3 times the natural log of x minus x evaluated from 1 to 3. So I have 2 pi times 3 the natural log of 3 minus 3 minus 3 times the natural log of 1 minus 1. And cleaning up a little bit, I now have 2 pi, 3 natural log of 3 times 3 natural log, minus 3 natural log of 1. I have minus 3, and then minus a negative 1 becomes plus, so that becomes a minus 2. I can combine my logs using rules of logs, so this becomes 2 pi times 3 the natural log of 3 minus 2. And we could plug that in and get an approximation, but we just want to see that the main trick here is we have to change our radius when we're not rotating around an axis. So we have 2 methods we can use to find volume. We have washers and discs versus shells. And so here we're just showing you a little bit of a comparison so you can kind of help you see when to use which one and how to set those up.